I'm sorry for the delay, but you know, if you don't know, this morning, yeah, it was a little tough. So, photography. Hello, is it recording or not?
Sí.
Okay. No. Yeah, photography. It's about a combination of two things. No, it's okay. I'm not going to start with the slides. Photography is about two things. So you have the technical part, which is how the camera works exactly, and you have to understand how the camera is made, what are the components, and actually what is the behavior of the light. So how the light works in order to be to manage your camera and to take good pictures. And another component, the second one, is about the art. So I can't learn you that. Actually, I'm not the right person to do that. I'm a software engineer, so I'll start with the technical part, and I will just explain a little bit how a camera works. But first of all, before going to see what are all these buttons here on this camera, and
I have a Canon. Oh.
yeah, of course. Canon are the best. I've been working with cameras for like 2 years, till 4 years ago. Now I'm a software developer, but I still remember something about photography. So I'll try to explain you something. I'll use this bumpers case here to demonstrate how like something camera-like. So for you to understand how the lights enter and what happens when you push the button. So I wanted to start with a video. Not this one. A video. You already know that I like very much this website, so it's TED.com. And like a week ago, I found a video where they explain actually how they they explain what their research has brought to. So there's a camera which can take 1 trillion frames per second. Okay, and in order to do that, they are going to explain how the light works, because you will see the video. Actually, they're going to explain it better than I do. So let's start.
It's really hard to explain it.
Doc Edgerton inspired us with awe and curiosity with this photo of a bullet piercing through an apple, an exposure just 1/1,000,000th of a second. But now, 50 years later, we can go 1,000,000 times faster and see the world not at 1,000,000 or 1,000,000,000, but 1 trillion frames per second. I present you a new type of photography, femtophotography, a new imaging technique so fast that you can create slow motion videos of light in motion. And with that, we can create cameras that can look around corners beyond line of sight or see inside our body without an X-ray, and really challenge what we mean by a camera. Now, if I take a laser pointer and turn it on and off in 1 trillionth of a second, which is several femtoseconds, I'll create a packet of photons barely 1 millimeter wide. And that packet of photons, that bullet, will travel at a speed of light, and again 1,000,000 times faster than an ordinary bullet. Now, if you take that bullet and take this packet of photons and fire into this bottle, how will those photons shatter into this bottle. How does light look in slow motion? Now the whole event Now remember, the whole event is effectively taking place in less than a nanosecond. That's how much time it takes for light to travel. But I'm slowing down in this video by a factor of 10 billion so you can see the light in motion. But Coca-Cola did not sponsor this research. Now there's a lot going on in this movie, so let me break this down and show you what's going on. So the pulse enters the bottle, our bullet, with a packet of photons. They start traveling through and they start scattering inside. Some of the light leaks, goes on the table, and you start seeing these ripples of waves. Many of the photons eventually reach the cap and then they explode in various directions. As you can see, there is a bubble of air and it's bouncing around inside. Meanwhile, the ripples are traveling on the table. And because of the reflections at the top, you'll see at the back of the bottle, after several frames, the reflections are focused. Now, if you take an ordinary bullet and let it go the same distance and slow down the video again by a factor of 10 billion, do you know how long you'll have to sit here to watch that movie? A day, a week, actually a whole year. A slow...
I'm sorry. Not too good. Okay, internet connection not the best. Where we were?
Now remember, the whole event is effectively taking place in less than a nanosecond. That's how much time it takes for light to travel. But I'm slowing down in this video by a factor of 10 billion so you can see the light in motion. But Coca-Cola did not sponsor this research.
So they have to wait for
Going on in this movie, so let me break this down and show you what's going on. So the pulse enters the bottle, our bullet, with a packet of photons. They start traveling through and they start scattering inside. Some of the light leaks, goes on the table, and you start seeing these ripples of waves. Many of the photons eventually reach the cap and then they explode in various directions. As you can see, there is a bubble of air and it's bouncing around inside. Meanwhile, the ripples are traveling on the table. And because of the reflections at the top, you'll see at the back of the bottle, after several frames, the reflections are focused. Now, if you take an ordinary bullet and let it go the same distance and slow down the video again by a factor of 10 billion, do you know how long you'll have to sit here to watch that movie? A day, a week, actually a whole year. It will be a very boring movie of a slow, ordinary bullet in motion. And what about some still life photography? You can watch the ripples again washing over the table, the tomato, and the wall in the back. It's like throwing a stone in a pond of water. By the way, this is how nature paints a photo, one femto frame at a time. But of course, our eye sees an integral composite. But if you look at this tomato one more time, you will notice as the light washes over the tomato, it continues to glow. It doesn't become dark. Why is that? Because the tomato is actually ripe, and the light is bouncing around inside the tomato, and it comes out after several trillionths of a second. So in the future, when this femto camera is in your camera phone, you might be able to go to a supermarket and check if the fruit is ripe without actually touching it. So how did my team at MIT create this camera? Now, as photographers, you know, if you take a short exposure photo, you get very little light. But we're going to go 1 billion times faster than your shortest exposure. So you're going to get hardly any light. So what we do is we send that bullet, those packet of photons, millions of times and record again and again with very clever synchronization. And from the gigabytes of data, we computationally weave together to create those femto videos I showed you. And we can take all that raw data and treat it in very interesting ways. So Superman can fly, some other heroes can become invisible, but what about a new power for a future superhero? To see around corners. The idea is that we're going to shine some light on the door, it's going to bounce, go inside the room, some of that is going to reflect back on the door and then back to the camera. And we're going to exploit this multiple bounces of light. And it's not science fiction, we have actually built it. On the left, you see our femto camera. There's a mannequin hidden behind a wall, and we're going to bounce light off the door. So after our paper was published in Nature Communication, it was highlighted by nature.com, and they created this animation. We're going to fire those bullets of light, and they're going to hit this wall. And because of the packet of the photons, they will scatter in all the directions, and some of them will reach our hidden mannequin, which in turn will again scatter that light. And again, in turn, the door will reflect some of that scattered light. And a tiny fraction of the photons will actually come back to the camera, but most interestingly, they will all arrive at a slightly different time slot. And because we have a camera that can run so fast, our femto camera, it has some unique abilities. It has a very good time resolution, and it can look at the world at the speed of light. And this way we know the distances, of course, to the door, but also to the hidden objects, but we don't know which point corresponds to which distance. By shining one laser, we can record one raw photo, which you look on the screen doesn't really make any sense. But then we're going to take a lot of such pictures, dozens of such pictures, put them together and try to analyze the multiple bounces of light. And from that, can we see the hidden object? Can we see it in full 3D? So this is our reconstruction. Now we have some ways to go before we take this outside the lab on the road, but in the future, we could create cars that avoid collision with what's around the bend. Or we can look for survivors in hazardous conditions by looking at light reflected through open windows. Or we can build endoscopes that can see deep inside the body around occluders, and also for cardioscopes. But of course, because of tissue and blood, this is quite challenging. So this is really a call for scientists to start thinking about femtophotography as really a new imaging modality to solve next generation of health imaging problems. Now, like Doc Edgerton, a scientist himself, science became art, an art of ultra-fast photography. And I realized that all the gigabytes of data that we're collecting every time is not just for scientific imaging, but we can also do a new form of computational photography with time-lapse and color coding. And when you look at those ripples, remember, the time between each of those ripples is only a few trillionth of a second. But there's also something funny going on here. When you look at the ripples under the cap, the ripples are moving away from us. The ripples should be moving towards us. What's going on here? It turns out, because we're recording nearly at the speed of light, we have strange effects. And Einstein would have loved to see this picture. The order at which events take place in the world appear in the camera with sometimes reversed order. So by applying the corresponding space and time warp, we can correct for this distortion. So whether it's for photography around corners, or creating next generation of health imaging, or creating new visualizations, since our invention, we have open sourced all the data and details on our website, and our hope is that the DIY, the creative, and the research community will show us that we should stop obsessing about the megapixels in cameras and start focusing on the next dimension in imaging. It's about time. Thank you.
Okay. So you've seen a movie, and you've seen what, actually, I hope that you understand what the light is. Was it interesting?
Very.
Yeah. Good. So, this is the point. Actually, I'll go in reverse order, so this was supposed to be the last video, the last thing to show you, but actually it's better if we do the slides now and then go outside and do it on open space, so that you can see some better pictures. I have the slides for these two arguments, so some technical aspects, which are zoom and flash, and the image composition, so the thirds rule, and how to express what you want to say with the picture. Actually, yeah, you saw a video where they were bouncing like a laser, a small piece of light, so a packet of photons, and the photons are coming back. Actually, with the flash, you do basically the same thing. So you send a lot of light in all the directions, not just laser, but in all the directions, and wait something to come back. So if I'm using the flash here, actually, and I point this camera to you, the light will expand as long as it goes on. So I'll have more light coming back from the persons in first row than I will have for the persons down there. Okay, so you will enlight much more what is in the foreground, and you will have almost no light for the background. Actually, there was a question on your questionnaires that we sent you, and we asked, would you use the flash to take a picture of the Eiffel Tower by night? Actually, the right answer is no, you will not. You will not, because the tower wouldn't get any light from your flash. You will just enlight the foreground, and that's it. So you have a lot of light in the beginning, and at the back you don't have any light. But actually you can use the flash by day 2. So the correct use of the flash, if I want to take a picture of Carlo without the flash, yeah, I'm looking because you are I have a lot of light from your back, and no, it's I'm not taking pictures of you. Come on. If I want to take a picture of Carlo, since I have a lot of light in the background, I wouldn't get any of his face. Okay, because our eyes can adapt to the light very quickly. So our eyes are much better than the camera that we have. because they can adapt, and we can concentrate on a detail and leave the other like uninterested. This is for the camera about the same, but the difference between our eyes and the camera is that the camera should take a picture, a whole at the same time. We, with our eyes, see like, if you take your thumb in front of you and you look to the thumb, this is like the dimension of the umbia. What's it called?
Nail.
The dimension of the nail is actually the dimension that you are able to focus on. So this is what you see really well. All the rest is blurry for your eyes and for your brain. So that's why you are going with the eyes all the times around. Okay, and this is the spot where you can focus the most. But the camera has to take all the picture together. So the camera has the same resolution in all the picture. Your eyes don't. Your eyes have like half of the sensor in the center, like in this spot, and half for all the rest. Okay. So the picture, when you're pointing a camera towards a subject, you don't want only the subject to be enlightened, but you want all the picture to be like almost the same enlightened. Okay, it depends. If you want to take a picture where you see everything, if you want to take an artistic picture, it doesn't matter, but you have to understand first what happens. So while the camera has to take a picture of everything, you should take care of the enlightenment of the whole environment. So if I'm going to take a picture of Carlo, I should use the flash. Without the flash, I wouldn't get any light from him, because the camera will take the average light and will take the light of the windows. So I will have the clear windows, and everything else will be dark. And this is an example. So without the flash, like in this case. So this is a better example than Carlo. Okay. Maybe nicer, I'm sorry. And if you use the flash, you will get some light from the front. If you don't, this is what you got. So you're not taking. Yeah, the projector isn't showing like the true picture because there's too much light here inside. But anyway, it helps. It doesn't help as much as by night, because the light of the flash is almost the same. It actually is the same by night or by day. But actually by day you have a lot of light from the environment, so the flash can't do that much difference. And by night it does. This is another example when you want to have some details, something in the shadows, then use the flash. So flash is not for pictures by night, actually. The flash is to enlighten what you have to enlighten in the foreground. Yes, in this case, actually I'm not seeing the true picture because, it's the light. Anyway, it's okay. If you want to take pictures of the environment, then you shouldn't use the flash, because the environment lights. This is a picture in London somewhere. You're going to have these details here, and you're going to have the environment light, which are much better than the light that you can have with the flash. So with the flash, what I would get? I would get this grass here very well enlightened, okay, before, but I wouldn't have any light for even the subject, because it's quite far. Okay, you will have like white grass here, then a little green grass here, and black grass here. Why? Why you will get these other lights? Because when you're taking a picture with your camera calculates the light that comes back to it. And when some light came back to the camera will adjust and will shorten the time of exposure. So you would get less light from anything else, because the flash is very intense light in a very short time. So you will have the light that you get with the flash has much more weight than the other light. So don't use it when you're outside. And this is an example of where you can use the flash. If you use this this setting on your camera, which is S-flash. It means slow, and it means that the camera will use just a small amount of flash, but will take care of all the lights, so it will unlock the exposure. So this is an example where I use the flash. So if you use the flash, use it, but with this implication, because you will have some more light in the foreground, but you will still get what is you have in the background. Without this, you would have only the subjects, and you would not have you wouldn't have anything in the background. Okay, so that's it about the flash. Any questions? Come on, save me. I have 10 minutes of slides. You have to be here for 2 hours. No, just kidding. Okay, what about the zoom? The zoom is actually what is changing what is the focal length. Okay, the focal length is, you know how it goes. It is, there is a camera. Okay, I'm really bad in writing in drawing, so I'll explain you just some basic things. If you have a camera, okay, this, and you have an objective that is short, like this, you have a subject here, and you have the light traveling and going like this. Okay? Actually, no, this is wrong, because this should be longer. Okay. The crossing, the crossing case in the objective here, in the middle. If you have a very, very long focal length, the focal length is the length between where is the sensor of your camera, which is here, okay, in the back, to where the crossing happens. So this is the focal length. Okay? The longer is the focal length, actually, the less light you will get. Okay? So this is another camera, and you have like a short focal length. What happens is that you have light going like that, so the focal length is much shorter. Okay, so it's this one, and it changes what you see in your picture. So the longer is the focal length, more narrow will be the picture. Okay, so you will take very little portion of the space with your camera. Okay, so this is my objective, and this is what you get. So you're getting really, really narrow. The point is that the light is the same in the room if you are going to take a picture of a small piece or of a big piece of the room. And actually, if you are going to have that light, all the light of the room coming into your objective, you're going to have one amount of light. If you're going to take the light coming just from that direction, so you have to zoom really, really far, then you will get much, much less light, because you get the same light, but only for this portion. Okay, and it has to be divided for the whole sensor, which is here. So you will get much, much less light. What happens when you zoom? So the stronger the zoom, the nearer seems to be the subject, but it seems to be. Okay, you are just along in the focal length, and you get this effect. So this is from far away. Took a picture of, this is the entrance of the University of Malta, and this one is zoomed but taken from the same place. Okay, I just elongated the focal length, but I had to adjust some more things, because you see that the exposure is almost the same. So you have ways to compensate this lack of light of the zoom, but be careful. Be careful, because the more you zoom, the faster the shutter speed should be. I'll explain you why in a few minutes. So this is the effect of the flash. But you could say, okay, but what if I don't have the flash? I can move further down. Actually, you will not get the same picture as zooming. Because if you move further down, so this is about the same picture, but this is taken from far away with zoom, and this one is taken from actually from here. Okay, so I moved really close to the subject. So you see, I took the picture from here. Okay, the second one was taken from here. You change the perspective. Okay, so if you look at the lines, while you're far away and you look to a building, the vertical lines are vertical. That's it. If you move near the subject and you just shorten this focal length, so you're zooming out, you have to adjust your camera a little bit towards the sky, which is the building. Okay, and while you're doing that, what happens? It happens that this part is a little bit closer to your camera than this one. So you'll get the effect of the road going away, like that. Okay? So you see that everything is going towards a point, and it's not going to be too strict. So if you're taking pictures of building, if you were studying architecture, this is very useful. If you want a picture with no distortions, you have to use the zoom. This is why when you're going to take a picture of yourself to put it on your passport, and the cameraman wouldn't get this close to you and take a picture of you, because otherwise you would have a lot of distortions. Okay? So if I take a picture from here and I make a portrait, I will zoom a little bit. Some numbers. Okay. Some numbers would be like this camera has 18 millimeters for the shortest, so the subjective 18 millimeters. And as maximum, I have 55 here. Okay? This is the focal length. So 18 is quite wide. So if I look through the objective with 18 millimeters, I get like from the door till the corner. Okay? I get all this space. Actually, if I zoom in, so 35, I would get like this portion. Okay? So, like that. This is the difference. So from the opening door to the corner to this one. You can have cameras which have much longer focal length. If you've seen like on the where you have some evening football games, and you see the photographers like with that big cameras. These are cameras which have long focal length, but since they have long focal length, so they're getting just a small amount of light, it is really hard to take a picture because you are getting just a small amount of light and you have to shut really fast because if the players are playing football game, they are not staying still, they are running. So you have to shorten the time of exposure of your camera. This is why they are wide. Okay? So if you see that objectives that are not only long to have focal length, but they also are wide to have more light. So as when you're buying a telescope, what is important is not how long they are. So the focal length, because telescopes are like this, are like the camera, they have focal length. Telescopes have 900 millimeters, like the one that you can buy for 200 euros, 300 euros. 900 millimeters is good enough, okay? But the quality of the telescope, it depends on how are they thick. Because the larger is the telescope, the more light you will get. And this is the same for the camera. So the larger is the objective. So if you get this one, you have an amount of light coming in from the lenses. If you have your mobile phone camera, you have another amount of light. Okay, that's why with this camera you can take pictures by night, right? With your mobile phone you can't, because you have to understand how it behaves, and you can see that the amount of light coming in here cannot be the same with the light coming in your mobile phone. Your mobile phone has some tricks, because there are different types of sensors. So that camera has a type of sensor and the mobile phone has another, but the quality of the picture is different. Okay, back to the zoom. So the stronger the zoom, the flatter seems to be the image. Okay, the subject that you're taking a picture of. So if you want things to just be to look like in real world, so to not be distorted, you have to zoom. When you're taking portraits, use the zoom. When you're taking picture of the buildings, zoom in. Okay. You zoom out only when you have you use like the 18 millimeters. Only when you have to take pictures of groups or something which is not quite regular, has no straight lines, because the straight lines will give you the distortion, and you will notice it. Actually, these are not true. Yeah, this is the true focal length, so it's at 18 millimeters. It means that the crossing of the light comes here somewhere, okay, very close to the sensor. So if here is the sensor, as is the 18 millimeters is like here. What else? Yes, cameras. The reflex cameras like this one. You can take off the objective, okay, and you can see what is inside. So here you have like a small mirror, okay, which enables you to look through this aperture here. And when you shot a picture, this mirror goes up for a millisecond and then turns down again. In this millisecond, you can see anything in here inside your mirror. Okay, so now I see you because the mirror is down. When I show the picture, the mirror goes up, it takes some light, it goes through the sensor on the sensor inside, and the sensor is going to memorize what happened, so the light which comes in. Some cameras, professional cameras, has a full dimension chip, full dimension sensor. That means that actually 18 millimeters. Yeah, if this is the sensor, okay, if it's big enough. Okay, sorry. If this is the sensors, and this, you will get the whole picture. Some cameras, like this one, which cost less than like 2,000 euros, they are faking, okay? So they are not getting you the whole chip. They are going to give you only a small part. So you will get this part. What does it mean? It means that if the focal length is 18 millimeters, you will get less of the picture, okay? So if I would have a 2,000 euros camera, I would get more of the 18 millimeters. I would get like that. But since the camera is cheaper and the chip is smaller, I will get a little bit less. So you have a factor when you buy a camera, and this factor is written in the specification. Actually, is 1.3. This means that you have to multiply the 18 times this factor to get the real equivalent focal length to a full factor chip. Good. So, what is next? Okay. This is a note about the camera. Actually, I have to explain some more things, but I don't have slide for this. So, I would better, since we are not that much, I can do the lecture here, and so I'll explain here. You have actually three other factors for the amount of light coming in your camera. So you have the zoom, okay, which is the focal length. Actually, the more you zoom, less light you will get. Also, if there's like 2 million photons in this room coming in my camera, and I just take a small portion of the field, I will get less photons coming into the camera itself. But we have also the shutter time. Okay, the time is how long this. Okay, this is called reflex because it's reflecting light in this mirror. So the time that the mirror is up is the shutter time. So the time that your sensor will get light. The longer is the time, more light you will get, because light is coming all the time. Okay, and the more time you use to have the shutter open, the more light you will get. Okay, but what happens if something is moving? If you have a moving subject, okay, you cannot shorten. You have to shorten your time, because otherwise you would get like something going away. You would have just the subject is sending light to the camera all the time. So your camera will have the information of the car here, but here as well. Okay, so you will have a continuous image of something crossing. You saw a lot of these pictures probably. So this is an effect of long time exposition, and this time exposition is used to have more light. Actually, yeah, another thing. Not only the subjects that are moving are going to be blurred, but also the whole image, because you cannot stay that still with your camera. Even if you hold your breath, you're shaking a little bit. So this shaking is going to affect your picture. So everything will be blurred if you're taking a picture with a long time exposition. If you're taking a very short time exposition, then it will be enough. So the rule is that the relation between those two is that time should be 1 on focal length. Okay? 1 on focal length. It means that if I have a 18mm camera, so it's like that, I can take a picture of 1/18th of the second standing still without having any blur on the image. While if I have a 200mm focal length, I would have to use 1 on 200 of a second, which is much shorter. Why? It's because, you know, if I take a picture of this room with an 18mm and I move like a 1/10 of the millimeter on the right, you wouldn't see the difference on the picture. And that's why. If I'm zooming that much, okay, I'm taking really narrow picture. So if I move half of the millimeter on the right, I change my subject. Okay? And that's why. So if your hands are shaking for half a millimeter, on a white picture, you have enough time to take an exposition a little longer. While if you're zooming, your exposition has to be much shorter. Okay, the length is good. What can I do first? Yeah, visibility, good. ISO. Okay, I'm not talking about the standard ISO. I'm talking about the sensibility of the camera. The sensibility of the camera is adjustable, so you can adjust your camera to use a certain sensibility, which usually goes from 100 to 3200. 3200, yeah. Okay, so if you're taking a picture with 100 ISO, 100 with 100 ISO, your camera will use a small amount of energy to take the picture because the light is very intense. If your camera uses the maximum of ISO, it means that it will concentrate all the energy to take as much as the camera can from the light that is coming inside. So it is amplifying much more the light that comes in. That's why if you are amplifying and you're an engineer, you know that you will get some noise out of the picture. It means that the less ISO you use, the better quality of the image will be. Okay, so less ISO, it means that you have a lot of light and you can do with this light just small amplification and store it, so it will be good. If you're using an amplification of the light really strong, your camera is not, okay, amplifying, like if I say, if this is the chip, the sensor, okay, and you will get like this amount of light, okay, on the first pixel, this amount of light on the second pixel, and this amount of light on the third pixel, and so on. Amplifying it. Okay, you don't have to amplify anything. This is good as it is, because if this is the maximum, so this is white and this is black. You have the black here and the white here. This is a good picture, okay? You have an average quantity of light. But if your camera sees something like that, so this one, okay, this one, and then this one, okay, this is not a good picture because everything is black, okay? You can compensate the ISO, so you can just enlarge it. So you will get the same picture, okay? You will amplify for a factor of, I don't know how much it is, but enough. Okay, you will get almost the same, but you cannot measure this one so well to amplify it correctly. So you will have something which is like this, but in reality it can be like this or like this. So you have something in this range. While in this case, you know that the measure is exactly this one. So you'll get some noise. So the light is, the picture that is taken from your camera has in this spot the amount of light between, I don't know, 2 points. And the more you amplify, the less accurate is the image. Okay? Because you're amplifying that much, the camera just doesn't know what is the color of that point, but it guesses. Okay, it's going to guess what it is. It's going to guess the digital. So you can't even, you know there will be some noise. So if you can, use the less number that you can. And then you have the last factor, ISO, and then you have the aperture. Okay, and this is why I'm taking this these blocks here. So, like small kids, okay, this is a Pampers box. If you it's not mine, by the way. So, if it's your camera and you do a small hole in here, okay, this is the hole, this is the camera, okay, and you have the sensor here on the back, so it's here, up here, okay? If you have the sensor here and some light coming from this small hole here, you will have the image projected on this back here. So imagine, did you brought the glasses? No, you didn't. Good, I'm going to draw it. Imagine, here, that this is the back of the box, okay, and you have a grid. This grid are the pixels of your camera, okay? Good. Okay, you have for each pixel a sensor. And each sensor is, let's say, independent from the other. It's not, but anyway, almost it is. And it takes care of measuring three informations. One for each color, so red, green, and blue. So for each pixel you have, it's divided in four actually, and you have two greens, one red and one blue. Why? Because green is more important for your eyes. Because when you're simulating the white, you are getting much more green than the other colors. That's why we like the green, actually. Imagine that you have this one on the back, okay? And you have a small hole here. Imagine that you have no lenses, okay? So you have the light coming in. Yeah, thank you, Alessandra, for the demo material. Where is Alessandra? Here. Okay, I was looking for you. Okay, so let's say that this is a ray of light, okay? Okay, which goes inside. You see that we have a small hole, okay, and the ray of light is projected on the back here. So the light coming from that corner down there is going to be projected on the corner up there. So it's the opposite. And the light coming from this corner up there is going to be projected down. See? Okay. So this is the one, and you will get like that. If the hole is small enough, you will get a perfect image without lenses. Okay? Because on each point, on each spot, on this array here of pixels, you will get the light from one point of the room. And that's it, because the light is going straight. It's not turning any corners. It is, but okay. But actually, you can imagine that it's not. Until very small holes, you will get almost as accurate as in the normal environment. While if the small hole is too small, the lights begin to behave in different ways. So I'm not going to explain that. If the hole is bigger, there is a problem. Because imagine that you have this pixel here, okay, and you're getting a hole this big. This pixel is going to get the light from that spot, but also of the whole range of spots around the room. So the image will not be accurate. This is why you have lenses. Okay? Lenses take only the light that is coming from one point and then project the image right here. So lenses are taking care that even if you have a very big aperture, you are getting the image projected on the back, so on the sensor. The point is that the smaller is the hole, the better is the image. But the smaller is a hole, the less light you will get. So you have to find a balance between it. With your camera, you can adjust the aperture. Okay? The aperture is how wide open will be the hole. If you take the hole very open, very big, okay, you will get much more light. Okay? But you will not have everything in focus. Because of of what I explained. So if the hole is really thin, you will have the same light coming straight exactly on the point that they should come. While with lenses, yes, you do the same with the big hole. So you are projecting the image there. But you cannot have everything on focus. This is the problem. This is the problem, but this is also good. Because you can take the pictures. I could take the picture of Alessandra, okay, and have everything blurred out, so I can see only Alessandra. This is done by opening the aperture very much. Okay, if I'm opening the aperture very much, I'm getting a lot of light, so I can do the best with the ISO and the best with the time. Okay, the best with the time is shorter time, so I can catch the instance. The instant of time where something is passing. So if I have to take a picture of a Formula 1 passing at 300 kilometers per hour, I will do my best. So I will open the aperture as much as I can. I should be taking care of the focus then, because if you have an aperture very small, then you don't have to care about the focus. You can take the focus even here, and you will get a perfect picture of the background as well. But have the aperture very open, then if I take the focus here, I will not see this point anymore. And you as well, you will be blurred out totally. So if I'm taking a picture of a Formula 1, I will take a very short time because it's passing really fast. I will amplify the ISO as much as I can without having too much noise. So I will put it like maximum is, take the maximum of your camera and divide it by 4. Okay. So if it's 3,200, like take a fourth of that. And if it's more, take a fourth of that. If you're going on half of that, you would get some noise. If you're going to amplify full, so you're using the maximum, the picture will not be as good. And if you pay, okay, it depends on how much you pay the camera. But even with your phone, if you see that if you take a picture by night, actually what you get is not a picture, it's some noise with some lights. Okay, that's it. So I'm opening the aperture for the Formula 1. I'm maximizing the ISO to have it amplified, and I'm taking a very short time. Because what is important is the time in this case. So you have to give more weight. Okay, the zoom, you can adjust it to have the image that you want. So this is art. Okay, let's divide it here. Art, and this is technical. Okay. So I'm going to explain you first here the technical part that you can use it best to take your picture, because everything is based on this. So if there's something in motion, you have to have the shortest time possible. If you're taking picture by night, you have to prolong this time, because otherwise you wouldn't get any. This one is giving you the noise. So if you are exaggerating here, you are getting noise. So this is noise. This is motion, and this is blue. Because aperture, if you have very big aperture, you're going to have a very short field where you're focused when you have the picture in focus. So aperture open, short field, short focus field. The focus field is the distance in which what you have is in focus. So if I take the focus on this bumper spots here, I have a field that goes actually from here to here. Everything between those two lines, so in this distance between like 1 and 2 meters, no, 1.5 and 2.5 meters from me will be perfectly on focus. Everything else nearer or more distant will be out of focus. Okay, if I take this aperture very small, okay, with my camera, like this one, then it doesn't care. It doesn't care anymore. I don't have to care anymore what's in focus, because everything will pass through a small hole and will be perfectly projected on the sensor. So if I take once again my focus on here with a small aperture, I will get everything in focus. Okay, so the field will go from like 20 centimeters from me till the infinite. Okay. So this is going to get you the blur of things out of focus. This is going to get you noise if you exaggerate, and this is going to give you the motion. So subjects in motion. Okay, I spoke enough. The rules of the thirds. We are passing on in the arc zone. So imagine that this is what you see through your camera. And most of the times your camera can digitally put these lines for you. So there is an input station in your camera where you can say, put me those lines, and those lines are the thirds line. It means that everything is divided in thirds. So you have in this way and in the other way. These lines are usually imaginary, but for our eyes are important. It's important because the crossing of those lines, so these points here, have the biggest result on your picture, so that they are getting a lot of weight of importance of your picture. If you put the subject here, then your subject will be important. If you put your subject here, then what is important is still what is here. Okay? So the center of the image is having a very much weight. So take care of it. While it's not a good composition to have your subject in the center, because actually it depends on what you want to say with your picture. If I want to take a picture of Alessandra, it's perfectly fine to put her here. Okay? But if I want to take a picture of you in front of a monument, it is not a good idea to put you here, because I want to say that you are in this place, not that you are. Okay? If I'm taking a picture of you in the center, I'm saying you are. Okay? Dot. That's it. That's what I want to say with this picture. If I put you here, I say you are in one place. Okay? And you give space to the other. So let's see some examples. Those thirds are used to divide the picture in zones, in some parts. Okay? So here you see two parts. Actually, it's not perfectly in thirds, but it doesn't matter. It's just the idea. So you have 1/3 and 2/3. Okay? Imagine that I understand. So where there are imaginary lines or physical lines, like the horizon or the cutting between two things, or there is a subject and something else, you would better cut the image on these lines. Okay, like in this case, this is the line where the image is cut. So you have two different types of background, on one and the other. Another example is here. So you use the thirds rule. So you have the thirds here and here representing the boat, and this one, and the center of the image and the rest representing the subject. Because I could have taken the picture of like the boat. Okay, but this is not what I meant. I meant that I'm going with this small boat to Valletta. Okay, so I took the picture and I want to give the much more importance to the background than to the subject, while still getting the balance. Okay, this is the rule of thirds. It doesn't really matter how if it's perfectly on thirds or not, but you have to have a right balance on the image composition. This is another one. So you see, there's a fisherman holding a fish, and there is a cat. Okay, so you have the same composition. You have like now. So you have the thirds here, and the subject here. But I'm not getting much importance. Since the subject here in the center is small, you are getting a very nice balance on the rest as well. Okay, what about the points? These points are the points where you have the most, the biggest weight of the picture. So in this case, this again me, and you can see that yes, it's divided in thirds, but actually you have the weight on these 2 points. Okay. I'm not in the center. This is what I meant. So you have to keep a right balance. This is another one. So the same thing. The aperture was wide open, so you see that I'm on focus. This is so and so on focus, but the background is totally blurred out. This is because of the aperture. While in this case, you have the background also on focus. So this is the difference on aperture. Actually, it's not only aperture. The zoom is doing his part as well. So the more you zoom, the smaller will be your field with some aperture. But anyway, it's important to understand the basics, then the rest comes with talking about this. Once again, so subject, 2 bicycles in the K points. Well, this one is just about the subject. So take care if you want to just take a picture of the boat, then take a picture of the boat. But it is a boat anywhere. It's not a boat in this place, it's not something going on. There's just a boat. I'm going to take a picture of the boat. This is the right point to put it. So here, you give it all the way. If you want to take a picture of some subjects, like I said, there is a good and bad example. Actually, it's not a bad example, but it's just not telling what I want to say with the picture. So I took the picture with of my friends, and I said, okay, we are in front of the church of Valletta, and then we gave the camera to a tourist and took a picture like that. And he wanted to say, oh, there's all of you together, okay? But it's not taking care of the environment. So this piece of road here doesn't, it's not interesting. Okay, it would be more interesting to see the top of the church. Or do whatever. So once again, thirds. So we are here, or just whatever you want to say. You can take fun picture. You don't have to follow these rules. This is not like hard-coded rules that if the picture is not taken like that, you will not get a picture. Much you will get. But you have to first express what you want to transmit with the picture, and do it in the best way. These are some guidelines, the thirds, and it's up to you if you want to follow them or not. And finally, yes, a friend of mine, tell your story. So if he wants to say that this is his new boat, he will just do like that, but I have to take the picture of him with the boat. If he's doing like that, nowhere, and I'm putting him in the center, then you can't understand that he is pointing to the boat. Okay, so I think that that's it. We're a little bit early, and we can go out and actually, do you have some questions? No? Are you sleepy? Yeah. Good. So So that's it. If you want, we can go a little bit out. At what time do you have to start from tobacco? It's 11:30. So it's midday. In half an hour.
I actually have one question.
Of course.
About the lenses. I never actually figured that out. We have the 18mm and the 55. What is actually the distance? I mean, what actually means? What it actually means with the 18mm or 55?
This is the distance between
The
the point. What?
The sensor and the lens, or what?
Yeah, the point. No, actually the lenses are making this crossing happen. Okay, if you have this hole, okay, and you have no lenses, the light is traveling through the hole and reaching your pixel here. So the crossing point of the light, where the light crosses, is here, and the focal length will be this one. Okay, this is the focal length. If you have the lenses, this hole is bigger. Okay, and somewhere between your lenses, which are like that, the light will be crossing in the same way. Okay, so the light will be crossing, and there is a crossing point, and this crossing point is the distance, is what you see with your number. So 18mm, it means that the crossing of the light here in my lenses, if the sensor is down here somewhere inside, the crossing happens here somewhere.
Oh, okay.
Okay, and the longer, actually, the more you zoom in, the more you move the lenses in such a way that the crossing begins further down. Okay, so the more you zoom, the farther is the crossing. But the crossing is the point of the crossing is that, imagine that, yes, this is the chip, okay, and this is the light from here. So I'm going to get the light from here to here, okay, on my chip, so on my sensor. If I zoom in, okay, like that, this is what I'm doing. So imagine that this box is not the camera, so I'm not moving the sensor. The sensor is staying here on the board. Okay, so imagine that that you are moving on the hole. Okay, if you move the hole further down, then what happens? It happens that if you are here, you are getting light of this field here. Okay, the light from this field here will go through the hole and go into the blackboard. If I'm zooming out, then the left, okay, I'm pointing always to the same corner, okay? So if now I'm pointing to that corner up there, it means that I will take a tableau in this picture. But if I go further down to point to the same corner, okay, I have to go almost straight. Okay, so I'm getting in that corner somewhere else, which is in this field. Okay? So the crossing point of the light is the distance. Is the distance of is the focal length. I'm sorry. That's it.
Thank you.
You're welcome.